adjustments in. Okay. So you have a cone and it has a point vertex, and then it has the top, and if we try to make a diagram of the cone, it should look like something. So this is the center, so let's say this is the vertex point, and so our cone should look like this. Okay. So we have this point vertex, it's called point A, and then we have this point in the center of the top of the cone. This is called point B. And you are all aware of the shape of a cone. It's a two-dimensional surface bent in certain shape, which is called cone. Okay. So the charge is uniformly distributed on this surface, and when the charge is uniformly distributed on a surface, the quantity that we express the charge in terms of is called surface charge density. And surface charge density is represented by this symbol, sigma. Okay. So what is a surface charge density? First, we need its definition, and it's defined as, let me use a different color. It's defined as sigma equals charge per unit area. Since every surface has some area, so it's defined as charge per unit area. The total charge distributed uniformly or non-uniformly over the entire surface divided by the total area of the surface is called surface charge density. And in this case, the charge is uniformly distributed over the surface. This uniformly distribution means that if I take two small patches, small area elements out of this surface, considering that they are equal in area, then the charge on these two small patches will also be equal. Okay, so if the charge, if the area of this small patch is dA and the charge on each small patch is dQ, then surface charge density can also be written in this form. And that's the good thing about surface charge density, because it's the constant quantity. Its value is same everywhere on the surface of the object, whatever you are considering, which in this case is cone. Okay. One thing. Now the thing that we are supposed to calculate, it's electric potential difference between point B, point A and point B. So what we want potential difference between point A and point B. This is what we want to calculate. And we know the formula for potential difference at any point. It's V equals integral of K dQ divided by R. Now we need to understand this formula, what it means, what are K is an electric constant, we don't need to worry about that, but dQ, what is this charge, and this curly R that I have used, what is this distance? We need to be careful about that. So in order to calculate electric fields or potentials due to continuous charge distributions like this distribution, like it's a extended object like a cone, or anything which is extended like you have a surface of the page, right? That's also a surface. So this is the charge that is uniformly distributed on that surface, and this is the total charge. And this dQ is the small amount of charge. Actually, it goes into the process of solving such kind of problems. Like when you have charge distributed over an extended surface, the way you solve it is like you consider small patch of that surface. In this case, we're gonna consider small area element because the surface is two-dimensional. And what we do then, integrate that charge on that small area over the entire surface, and so which means that we are including the contribution from all surface. Okay, so that's the procedure. So we need to consider small area elements. So in case of this two-dimensional surface, which is cone in this case, let's say we take this kind of small area element. So this is my small area element. So it's like goes around the cone. Okay, and if this distance from the center, if this distance is r. That's how we define it, like the distance from center to one side of the cone. Let me define this distance as r. This is the curly r that we need. Why? Because we want potential at point A, okay, and this distance, this is where surface is. This inner region, it's empty, we don't have a surface. I'm just defining this distance as r, which goes from center, let me erase this side, which goes from center to this point, okay. And then this small distance, it's gonna be dr. Actually dr is gonna show up in that formula, I'm gonna show you in a moment. So this distance is gonna be dr. Yes, yeah, because we want to calculate potential at this point, okay. So this strip, it has some amount of charge on it, and that charge is, that's this charge dq here in the formula, okay. So what I'm assuming that I have taken this small area element at some point on the surface of the cone, okay, and I want to calculate the total charge on this one and the total area of this one, because that's what I need. Charge, this from this definition, it can be written as surface charge density times total area, okay. If you want to calculate the value of dq, you just multiplied both sides by dA. So dq is equal to sigma dA. So this formula takes the form integral k, it's constant, take it out of the integral, then it would be sigma times dA divided by curly r, okay. So we need the area of this green patch that we have taken, okay. So how do we calculate the area of this green patch? So I have defined this distance r. This is the radius, radial distance from the center of the cone to surface of the cone. So if it's not a cone, if it's a cylinder, what's the area element of a cylinder? Just 2 pi r dr, okay. So in this case, since this length of the top line is greater than the length of the bottom line, so what I'm saying is, if you calculate the distance from this point to this point, you see the top line has bigger length because the cone and cone is opening up. So if I draw two parallel lines, the top line is going to have more length, okay. So this, in order to calculate this dA, if you look at this small patch, which is greater in this case, this kind of makes a right angle triangle, and this side is the one that we are looking for. This is dr, okay. We know the length of this side, this is r, this is exactly what we have defined, and we also know that this angle is 45 degrees. So we can calculate dr, we can find a relation between r, curly r, and dr, okay. So if I write this formula for potential, this takes the form V equals K times integral sigma. So sigma is also constant, let's take it out of the integral, and now we have dA. So this becomes 2 pi r d curly r divided by r. So we have everything. This is the main formula that we are going to use the potential to calculate the potential. But in order to compute this integral, we need to have one variable on which we are gonna evaluate this integral, okay. But inside integral, we can see we have two variables. This r, this is the regular r, I'm gonna call it r, and this is the curly r, okay. So you need to find a relation between these two r's, okay, and this is precisely what I was doing here. This gives you the relation. And if you look at this triangle, this angle is 45 degrees. So it's sine theta if this angle is 45. So from here we will have sine 45 degrees equals r divided by curly r. That's just the definition of sine theta in a right angle triangle, okay. And from sine 45 is 1 square root 1 divided by square root 2, and from here we find that this small r equals curly r divided by square root 2, okay. So this is my choice. You can substitute one variable in terms of the other, that's your freedom. But I have kept the curly r because I already have dr, d curly r. So in order to make my life easier, I'm choosing this. Otherwise, if I substitute it in terms of small r, then I have to take derivative of this equation to, so that I could substitute for this d curly r too. That's your freedom, but I'm going to stick with this one. And so our formula for potential becomes K sigma, then we have 2 pi out, and then we have 1 divided by square root 2 out, and now we have integral r dr divided by r. Okay, we good?
The curly r's would cancel out.
Curly r's cancel out, and we have just integral over r. So this is 2 pi sigma k divided by square root 2 integral over dr. So now the next question is, what are the integration limits? Okay. So this is the surface that you are integrating on. It's the side of the cone. And if you want to find the potential at point A, this point lies at the origin. So your cone starts from here. Okay. And at this point, the value of curly r is just 0 because r is going in this direction. That's how we defined it. So lower limit is 0. What about the upper limit? It goes till this point. What will be the upper limit? This height is given. This is h, total height. This is also given. It's also h. Okay. So it's just a right angle triangle. So h square plus h square square root 2h square. And if you take just r, so this will be square root 2h. Right. And so you can calculate, this is actually the potential at point A. Since the time I substituted this r, this becomes potential at point A. Okay. And so this turns out to be just square root 2 h, and this becomes 2 pi sigma k h. And if you wish, this can be written as sigma h divided by 2 epsilon naught. This is the potential at point A. We also need the potential at point B. And that's kind of going to make our life miserable, but we have to do it. Okay. Now we have small area element of this cone, and we want to find the potential at point B at this point. Okay, what the r, curly r in this case will be, because we have the same formula for potential. Where is it? Here. So we have dA. The only thing that we don't know this curly r, because this is the distance from the point at which your small surface area is to the point where you want to calculate the potential. So here was our small surface area, and this was the point where we wanted to calculate potential. So this is the distance that I defined as curly r. Now our surface area, small surface area, is at the same point, but we want to calculate potential at point B. So this r is in general gonna be different, and so we represent it with a different color, and let's say this is the distance. Okay, because that's the distance to point B. And since we have already used symbol r, let's call it r prime. So in this case, our formula for potential becomes V at point B. V at point B, it's K times sigma integral limits. Now we know the limits 0 to 2h because the cone is the same object for both of these points, so limits should stay same. And then we have dA, which is 2 pi r dr. So this will becomes 2 pi r dr prime divided by r prime, right? Just the r changed. The distance to point B is different from than point B. We good till this point? Okay, how do we calculate r prime? Here's the diagram. How do we calculate it? So you want to write r prime in terms of quantities that we know. Okay, so what do we know? We know, yes, please go ahead.
We know R.
Which R? There are many R's.
The regular R.
The regular R, good. We also know curly R. So these are, and we somehow know H too if we have to, because if we consider this side, this is total height of the cone. Okay, so we know H, we know the regular R and the curly R. So these are the quantities in terms of which we can express this curly R prime. Okay, so there are many ways you can just consider this small right angle triangle. The way I did it, I considered this not right angle triangle, some ugly little triangle, and what I need is R. So here's what I have. I have the height of this triangle. I have this distance, which is curly R, okay, and this is the distance that we require. And we also know this angle 45. Do you remember if your triangle is not right angled triangle, how do you calculate one side of that triangle?
Use laws of sine.
Law of cosines. Okay, remember law of cosines. I'm gonna write for this one. So R prime, curly R prime, this will be, we have square root, this will be h square plus R squared minus 2 R h cos of 45, right? And this can be written as h square plus R square minus square root of 2 R h. That's it. We have found curly R in terms of we have found curly R prime in terms of curly R. Okay, we have one factor of this regular R, but we already know that. Where did we calculate it? Here. So now our variable is curly R, so we can integrate over curly R. Okay, so again we have brought our problem back to this integral and the same variable curly R, but the overall shape of the integral is going to be much different and maybe harder. So let's see. So let's substitute this R, curly R prime, in this and the value of this regular R. So VB will be 2 pi a sigma integral. R was R times square root 2, so I'm going to bring square root 2 outside, and this will be R d R divided by square root of h square plus R squared minus square root 2 RH. That's it. How we are going to solve that? I have also changed one more thing from dr prime in the top integral to just dr. How can I do that? As long as we are considering the same area element, this dr is the same. So since for consistency, since I took the distance r prime this time, so I used in one step dr prime, but we know that dr prime is actually dr. Okay. Good. How we are going to solve this integral? This is a horrible looking integral. Took some time to solve it. So we are going to complete the square on the bottom, because this equation in the denominator is a quadratic in R, curly R. Okay. So if we complete the square, I'm just gonna do it here. So this becomes curly R minus h divided by square root of 2 is whole square plus this h square minus h divided by square root 2 square. And now I wish so much that I could just copy paste it at the bottom, because I was going to use that side. Anyway, you see how did I do it? I just added a factor of h square by 2 and subtracted a factor of h square by 2. I did nothing. But when I add the factor of h square by 2, this factor, this term becomes square of this whole term. And this h square is here, and the subtracted factor of h square by 2 is there. Okay. So this actually becomes this square plus h square by 2. Okay. In other words, h square by square root 2. So I'm going to write that here. So 2 pi k sigma divided by square root 2 integral of RDR divided by R minus h divided by square root 2 whole square plus h divided by square root 2 whole square. That's my integral now. And square root. Now what do you think you can do with this? How we can try and solve this one? Any idea? What's the simplest thing that comes into your mind after looking at this integral? Yes.
Trigonometry?
Yeah, trigonometry. We can also do some
Substitute.
substitution. Okay, that makes our life easier. So I'm going to do that for now. So let's substitute t equals this term. Okay, so we do t equals r minus h by square root 2. So what that dt will be? Dt will be dr, right? It's simple enough. I'm going to erase this line. It's done. It's not needed anymore, so that I could move to.
I have a question.
Yes, please.
Come from Griffiths.
Maybe.
Okay, but it's on the class discussion page.
No.
Okay.
I realized I can only make announcement on professor's page.
Okay.
So you got the email, which announcement of the email that I made regarding office hours. Yeah, I tried to upload it, but I had no option to upload documents because that page is controlled by your teacher. Okay, but maybe Griffith has a lot of problems, so it might be. But he gave me the worksheet. It was not mentioned on that this problem is from Griffith. Yeah. Okay, so let's do this substitution, and this will become v at point B equals 2 pi sigma k divided by square root 2, and then r will become t plus h by square root 2, dr will become dt, and this becomes t square plus h divided by square root 2 whole square and then whole square root. Okay, right, that's substitution. In the next step, now you see we have sum of two terms in the numerator, so you can expand this one integral into two to make our life a little easier. So let's write this 2 pi sigma k divided by square root 2. Now it's being multiplied with two terms. So first will be t dt divided by t square plus h by square root 2 square whole square root, and the second term will be where's the integral, and second term will be plus h by square root 2. I think I'm going out of. Second term will be h by square root 2 integral dt divided by t square, yes, t square plus h by square root 2 square whole square root. That's it. So we have to solve these two integrals to get the answer. Okay, which region we should go and erase now? This one or this one? We're eventually going to need both of them, so let's start with the left. I didn't want to erase the statement and the diagram, but it's okay at this point. Okay, so Let's compute the integrals one by one. And also remember that since we have made this substitution, we also need to take care of the limits. Okay, limits should also now our variable is t, and so we have to find limits for t. I'm going to come back to that in a moment and do that, but first let's take the first integral. I'm going to forget about this constant for the moment, or let's call it a. Let's call it a. So first integral, this is VB equals a times RdR, which is t dt divided by t square plus right, this is correct. Yes. Okay, so let's substitute t equals t square plus h divided by square root 2. Is it a good choice? I mean, it's going to work eventually. Doesn't really matter. So dp will be, no, this is not a good choice.
I think you have to square the h divided by square root 2.
Yeah, that is fine. Let me look at my notes. This was supposed to be simple. Yeah, anyway, I did the same substitution. It just is solved. So dp will be 2t dt, right? And we need the value of t dt, so this becomes dp divided by 2 equals t dt. So this integral becomes vb equals a integral, so this dp by 2 will give us a divided by 2, and so dp by square root of p. Yes?
I understand everything, but I just don't understand. Like everything below the p, it makes sense if you say p is equal to that, but I don't understand why you chose that for p.
Well, you learn these things with experience. Uh,
It's like you're trying to.
it's just substitution. You can actually substitute t equals h divided by square root 2 times tan theta, and you can solve it here. I'm going to do that with that integral.
Okay.
But these are the techniques of calculus which I learned during high school or college, but that's how you solve. Like this is a standard form of an integral. In my math book, it was like how to solve the integrals of this kind. Okay, so I made substitutions, 2 times substitution. At this point, you don't really need to make a substitution anymore. You can just use here let t equals h divided by square root 2 tan phi. What the t square will be? H square by 2 tan square phi. Right? You take h square by 2 common out of this square root, and this becomes 1 plus tan square phi, which is secant square phi. And then here in the numerator, you will have secant phi, secant square phi d phi. So you can just solve the problem from here, but one more substitution makes it very simple. But these are techniques of, and that's why, that was the one reason why I wanted to solve this problem in its entirety, so that you would know that there's intuitive part in which you figure out your problem, that how I am going to solve this problem, and then comes the mathematical part that you actually have to compute and to get a mathematical answer. Okay? Sure. So now this will give us a divided by 2, and this will, the integral will be p power and then the limits. You know how this integral is computed? Now let me write that stuff then. This is a general form of integral, so this becomes p power minus 1 by 2 dp, and this is a divided by 2. The integral of this factor is simply p power minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. This is the first thing that they tell you, that if you have a function like integral x power n dx, then its integral is x power n plus 1 divided by n plus 1, yeah, plus some constant. If you have integration limits, then you don't need the constant. This is like the first thing that they tell you. I mean, I'm not saying that they tell you, actually they prove it in calculus mathematics, high school or college mathematics, but that's the simple formula. At this point, you can just remember the formula, how to do them. Okay, so now the integration limits. So we have changed our variable 2 times from originally r to that p. Once we went to t and then we went to p. So when we went to t here, our limit was from 0 up to square root 2h. So if we substitute r equals 0, t becomes minus h by square root 2. And when we substitute r equals square root 2h, so t goes to minus h by square root 2, and the other one becomes plus h by square root 2. You can put r here, this value square root 2h, and this will becomes plus h by square root 2. So that's the limits on t. Then we substituted p for t, and now we want to calculate the value of limits of p. So when t is minus h by square root 2, minus h by square root 2, this becomes h square by 2, doesn't really matter. This becomes minus h by square root 2 square plus h by square root 2 square. This is our first limit. This gives you what it gives you, h square by 2 plus h square by 2 becomes h square. When you put t equals h by 2, this gives you h by under root 2 square plus h by under root 2 square h square. So the upper and lower limits turn out to be same, and if the upper and lower limits are same, this is going to give you 0. So this integral gives us 0. Now we have to compute the second integral. Okay, and for that I have to erase this one. Just remember this value for point potential at point A, and the second integral is VB. We have constant A with us, and then from second integral we have a factor of h divided by square root 2, so this will be h divided by square root 2, and then we have integral dt divided by t square plus h divided by square root 2 whole square square root. Yeah, this one is easier one. This is like the one that I was telling you. You can directly substitute. Let's call this term for the moment A. Okay, it's a good symbol. Okay, so our A is h divided by square root 2. Okay, so in order to solve this integral, you can substitute t equals a tan phi, and so dt will be a, it's constant, and derivative of tan is secant square phi d phi. So this becomes VB equals a h divided by square root 2 integral of dt, it is a secant square phi d phi divided by t was tan square, so this becomes a square tan square phi plus a square whole square root. You can take a square common, and since we have a square root over the entire term, this will become integral a secant square phi d phi divided by a into 1 plus tan square phi. This term 1 plus tan square phi, this is equal to secant square phi, and its square root will just give us secant phi. So then this a cancels out, so this entire term becomes a h divided by square root 2 integral of secant square phi d phi divided by secant phi. And one secant goes away and we are just left with the integral of secant. So VB AH divided by square root 2 integral of secant phi d phi, and integral of secant, I'm gonna again just throw an integral on you at you. This is gonna be secant phi plus tan phi, and then the limits which we need to find. That is actually the natural log of this factor. This is the integral of secant phi. If you're stuck on these things, I believe if you are in exam, even Professor Hammerling will tell you, because they don't bother about these things. These are general formulas. And if you're doing homeworks, you can always look these things up on internet. These are general integrals. Okay. Let me check, is it secant phi plus tan phi or tan phi plus secant phi? Yeah, it's a secant plus tan. Okay, good. So again, we have changed our integration variable from t to phi. We need to calculate the limits. Remember the limits of t that I calculated here? They were minus h divided by square root 2 to plus h divided by square root 2. Okay. And now I need to calculate the limits of phi. Where did I substitute t for phi? Here. So from this equation, phi turns out to be tan inverse t divided by a, and this is a. So for lower limit, when t is minus h by square root 2, this will become minus h divided by square root 2 divided by this a is also h divided by square root 2. So this becomes tan inverse minus 1. Good? Tan inverse minus 1 is minus 45 degrees. So I'm going to write it as minus pi by 4 degrees. Pi by 4 radian, sorry. And if I substitute t equals plus h by square root 2, this just becomes tan inverse plus 1. And tan inverse plus 1 is plus pi by 4. Okay. So we have the limits on phi. So let's substitute these limits in here. So this equation becomes VB equals AH divided by square root 2 natural log of secant 45 and secant minus 45 both gives us the same value, square root 2. Okay. So this becomes square root 2, and tan 45 gives us plus 1, and then square root 2 and tan minus 45 gives us minus 1. So this is what we get. And I have skipped one step. Can you see what I have done? So generally when you substitute the limits, you substitute the upper limit minus you substitute the lower limit. Okay. So this will becomes natural log of, this is the upper limit, minus natural log of, this is the lower limit. But then you have the general formula that natural log of A minus natural log of B is just natural log of A by B. That's what I have done. Okay, we have solved the problem. Let's substitute back this factor, and this factor was equal to, anyone remembers it? Oh, there is one more thing. No, there's no more thing. Okay, do you remember this factor? It was 2 pi sigma k divided by square root 2. Did we have square root 2?
Yeah.
Okay, h divided by square root 2 and this factor. This constants goes away, 2's goes away. There should be one more factor of 1 by 2. Where did we miss it? I have missed one factor of 1 by 2. No, I haven't. No, I haven't. Okay. So this is potential at point B. We need potential difference between these 2 points. So VA minus VB. VA was sigma h divided by 2 epsilon naught. This is sigma h divided by 4 epsilon naught into factor of this natural log of square root 2 plus 1 divided by square root 2 minus 1. Okay, so you can take this factor common. This becomes sigma h divided by 2 epsilon naught, and this becomes 1 from here minus 1 by 2 from here, and then natural log of square root 2 plus 1 divided by square root 2 minus 1 mod. This is the absolute value. Absolute value, and then we close the brackets. That's the answer. You can simplify it one more step. A little very common property of log. This becomes, I mean, if you wish, otherwise this is the answer. Divided by 2 epsilon naught 1 minus this 1 by 2 actually goes into the power of natural log. If you remember, square root 2 plus 1 divided by square root 2 minus 1 power 1 by 2, and this is 1 by 2 is whole square root. So you can just, this is 1.4142, this is 1.4142 minus 1, so you can compute these things and your answer can even be simplified in this form. 1 minus natural log of square root 2 plus 1. So you can also write it in this form if you want. But this was the entire exercise, just to remind you that things are gonna be lengthy now, things are gonna be harder. Just prepare yourself for that. Actually, I was checking the homeworks and I saw people as if they were not ready to solve a problem in more than 5 lines. You have seen this one. And this is like a mid-range problem. There can be harder. I saw one harder problem on your second homework. So just it's more about making your mind that it's okay that if you use like 4 pages to solve a problem, they are like this. Questions?